Swayam Prabha. Digital India. Educated India.
So let's continue with our lecture. So we have introduced the complex CFD-DEM for simulation of debit flow. Typically, we use unresolved CFD-DEM for that purpose. And then we then introduce a different coupling scheme like this semi-resolved, fully resolved, and essentially that we typically we use a hybrid resolved, semi-resolved, and including unresolved, and have them together, and then for a more practical prediction. And we follow that line of approach, coupling CFD-DEM, and then we tackle another very interesting topic. Is how we can simulate laser powder bed fusion, so L-PBF, for additive manufacturing here. So what is L-PBF, laser powder bed fusion? Probably a lot of you have really to read this before, for example. So this is a demonstration, and then you have a layer of metallic powder or other kind of powders here, and you use that laser to melt part of that and form a certain structure. And then this is a typical laser powder matters. And then there's another companion technology called a DED, directed energy deposition. It's also part of this laser thing here. Basically, you spray the metal powder, and then when the powder is just in the air, use the laser to melt it, and then to deposit in a place that you want to form a part here. Okay, so the material costs not only metal powders, but you can also use polymers, biomaterials, and other photosensitive material for their printing. You can use a laser beam, you can use electron beams, and ultraviolet lasers or other method, physical method here. Okay, the way for the deposition, you can use the fusion. You can also use a photo polymerization and also laminate or extrusion method for you. Okay, so the additive manufacturing basically have a different ways, quite a variety of ways, but for the printing purpose here. Right, so that is the additive manufacturing, typically the laser powder bed fusion works like here. And now the laser powder bed fusion technology has been quite popular for advanced manufacturing, because we want to build high strength and expensive parts like the rocket engine and the airplane engines and other things, and then this L-PBF can be quite a popular way to do that here. On the left is another illustration that we have an incident laser, and then on the bottom, basically a layer of this metal powders here. And this laser will melt the powder and then generate a very high energy source and melt the powder into a liquid form. When the liquid cool down, will be further solidified into a metal, high-strength metal again here, right? So this is how the L-PBF works, and this is how related to the granulometer thing here. Essentially, here this is roller, and then this is the powder. You have a storage compartment, and then you use this roller, basically roll a one layer of this metal powders into this work area, and then you ladder this laser to illuminate it and to melt a certain depth of these metals here, and then you use this roller to really to spread another layer of this metal again to do this in a repeated way here. Okay, and so that is how this laser powder bed fusion works here. Right? And as I mentioned, basically, we can really to use this technology to fabricate a very complex part with irregular shapes and with very composite structures. If you use other technologies, it's either very challenging or is possible. For example, you want to print a very small part, and then like this one, this is the head link and cool electronic chips, and then this can be printed by this laser melting technology here. Okay, this is another example that this show that we can really optimize the design and then to print some parts in a quite creative way, which is conventional manufacturing cannot possibly finish here. And the laser powder fusion technology, they could have a different ways to do that here. Okay, for example, we can really do a so-called bi-material selective laser sintering. So this is a relatively conventional way. Essentially, for example, you have two kinds of material. One is the copper particles. The other is the steel particles here. Okay, and we know the copper particles, their melting point is some relatively lower than these steel particles. And then we use a laser or other heating source, basically to melt the copper particle first, and then this copper particle melted, and then there will be form a bond, fill the pores connected to the hard particles, steel particles. And this is we call it selective laser sintering technology. Sorry, and then if we don't do this sintering means that we only melt part of this particle, not the whole of them. And then the needed power or temperature is not high because it really depends on the lower melting point material. But eventually melt a whole material. This is what we call a selective laser melting. Basically, melt all the material here. Okay, and so in both ways, you can see this selective laser sintering. You can create bigger pores. The pores can really to significantly lower down the strength, and so this is even though it's conventionally is easier, but it's basically it's not preferred to manufacture very high strength part here. And even for the laser melting, selective laser melting technology, and then they can generally help us really to generate high strength metals, alloy, and then but essentially the big part also can leave some porosity. This porosity can be quite a major defect that affect the performance and even failure of the part here. Okay, of course the other things that are for this different technologies that are you do melting, and then sometimes that only some particles partially melt, and then the other part or some particle is left unmelted here, and this will generate the different surface roughness or so-called balding effect here, and then this one will affect the performance because sometimes the surface smoothness or roughness is pretty critical for certain kind of need here. And so that is another requirement that when we really print use a selected laser printing technology. And then, so as I mentioned, that for the melting, selected laser melting technology, and then we wanted to eliminate the defect, including the porosity, including the surface, want to make the surface roughness or surface smoothness can be very meet certain criteria here. Okay, so how can we do that here? So that is a question indeed. That's the challenge posed for this laser additive manufacturing here. And then so how traditionally now the current practice works to eliminate to reduce the porosity, reduce the defect, reduce the surface roughness. and they typically do this trial and error, right? Okay, and they try different laser power source and try different printing speed and this kind of thing and do trial and error. And this is quite expensive. And normally, the laser melting and you need quite a high energy. And if you want to print an expensive part, and then it's not affordable really to do this trial and error things here, right? And so that's a traditional way here. And then a preferred way is that we can develop a advanced computational approach and try to simulate and replicate the process, understand the physics, and try to find a way and to understand how the defect or porosity is formed, and then we can develop a strategy to optimize the printing process to try to avoid the defect. And in that way, we can really achieve the quite similar purpose and then remain cost effective here. But simulating this laser powder bed fusion is a challenge because the whole process is a dynamic multi-physics process here. As you can see, we have laser beam, okay, and laser beam when it is illuminated to the powder, and the powder will be melted into the so-called multiple, okay, multiple liquid, and this multiple liquid itself can be further evaporated, become a metal vapor, and this metal vapor, the speed can be high, and then it itself can be to interact with the particles with the surrounding air if it is not in a vacuum condition. Okay, in the process, and we have a lot of physics play in an important role. For example, you have this recoil pressure, we have absorption, energy absorption, refraction, and heat convection, and then the particle lines, you have splashing and spattering here, okay, and also heat radiation, okay. And for the metal pole, you have also evaporation, Maragoni convection, and phase transition here. And then because you change the particle into liquid, and also it's not you have capillary effect during the inside the particle as well here. And part of this one also including this sintering process, and you have gravity force to consider. So you can see that it is a very complex challenge, multi-physics process involved. So make the simulation is extremely challenging here. Okay, and summarize that, indeed, essentially, if you want to simulate this L-PBF, you need to consider at least 4 interactions and heat transfer among the metal liquid flow, we call the molten pole, and this metallic vapor, and then ambient gas if it's not in vacuum, and solid particles here. Okay, and these are 4 phases because at the beginning we have only metal powder with a solid state, but it will experience melting, and then when the metal liquid cool down, it experience solidification, and also the metal liquid can become evaporation, and also the powder particle to metal flow and to metal vapors. So this is very complicated multi-way phase transformation. Okay, and we need to consider that here. And also it's a multi-phase interaction. It's apparently you have a solid particle, and then you have a spattering and a splashing complex flow, and a vapor flow, gas flow, as well as this liquid flow, right? And also the physics is complicated. It involves the heat conduction, convection, radiation, absorption, and we need to consider recoil pressure, Maragoni pressure, flow drag, turbulent vertex, and also capillary force. So they summarize all the challenges we need to consider in such a simulation. Okay, and so what did the existing method do? Basically, the existing method involve using finite element method or CFD for that purpose. Those are the published results that are available. Even one published in I think in Science. And basically, they cannot really to account for all the things like including powder motion and how the vapor and matter flow affect powder motion here. In that way, and then we need to consider a DEM because we know that DEM is very good at modeling the particles here. Okay, and then so the better ways that are for pure FEM or CFD alone, you cannot consider powder motion, and you need to incorporate your DEM, couple with DEM to consider that. So this is the way that we choose to use the coupled CFD-DEM to simulate this L-PBF process here, right? We essentially want to capture these four-way interactions and heat transfer as I mentioned before, right? And we still use this the carbon scheme that we mentioned before. We selectively use the fully resolved coupled CFD-DEM, unresolved CFD-DEM, semi-resolved CFD-DEM, and then in certain ways, and we selectively use the hybrid one. Okay, and I will show that in what process we choose which one really for the purpose here. And essentially, how we do that. And we consider a three-phase CFD simulation here. Three-phase means that for the melt liquid, it's basically liquid phase. And also we consider metallic vapor and also the gas, ambient gas. So we have two phases of air phase and one phase of this liquid phase here. Okay. And for the powder layering process, and we can only use pure DEM, and we simulated the roller, and then for the layering process, for example, this can be done under for the layering process and this pure DEM simulations, or we can use the unresolved CFD-DEM for certain situations where we want to consider also some air phase and out phase take place here, right? Okay. Or for example, and if layering process also involve part of the liquid and at the lower bed, and then we can really use the coupled one here. But for convenience, normally people use DEM, pure DEM for layering process here. And then to resolve the temperature field, and then we develop a so-called semi-coupled CFD-DEM. I will show that what is a semi-coupled. Don't be mixed this with the semi-resolved is different here. Okay, and also it's important really to resolve this laser source model more accurately. So we develop a high resolution ray tracing laser model for the laser elimination, because different laser model elimination will cause different energy absorption, and you can generate quite a different results here. Okay, and then for the following process, how the powder is melted, evaporated, and how the multiple liquid flow and interact with the keyhole and the powder motion, and we use a fully resolved CFD-DEM for that purpose here. Okay, so essentially this will be tackled within a very comprehensive coupled CFD-DEM framework. Let me show you how we can really to do that here. So we consider four-phase CFD-DEM model. Okay, and the DEM considers solid powders, and then it involves a volume fraction of causes porous medium. And the three-phase CFD consider we based on volume of fluid method and consider the melt flow. We can also consider partially melted powder. Okay, and we also consider metallic vapor, which is a evaporated, which when there's a melt liquid and evaporated become vapor air, and also we consider the ambient gas. Okay, so those are the three phases CFD here. And then the semi-coupled, and then the way that I will show that how we can really consider the partial melting thing here. And then for the powder layering process, we can typically use the unresolved CFD-DEM for that purpose, right? Okay, and then for the melting process, again, that we use fully resolved CFD, and then in conjunction with this immersed boundary method IBM, and to fully resolve that one here. And so the safety cell we have mentioned before here. These are the governing equations, including the DM equations for Newton's law of motion for the particles, and also the energy, the advection equations, and the momentum equations, temperature equations. So I won't really go to detail of the equation or each equation represent. But here I want to introduce the so-called semi-coupled CFD-DEM. So what is semi-coupled? So it's different than a semi-resolved. Semi-resolved I introduced before, essentially want to capture a intermediate case where we have a CFD cell is comparable to the particle size, right? That's called a semi-resolved. And essentially we propose the interpolation kernel function to do the interpolation and to the surrounding cells here. But here the semi-coupled CFD-DEM mean that we want to model the melting of a metallic powder. But for example, if the two powders are subject to this laser illumination, and their temperature increased, and typically at the top, and then temperature will rise fast than the bottom. And so you are going to have a gradient of this temperature field for each individual single particle. And then this will create a progressive melting process, or and then sometimes some particle, because this progressive melting, and then it's only partially melt and leave the other part a solid part here. Okay, and if we treat that purely in DM, of course there's still technical to do that. And then for each DM particle, I'm going to do this high resolution temperature field simulations. And you can use the other technique, for example, each individual particle, you just use FEM to discretize this domain and then to simulate the heat field. That will be computationally too expensive to afford here. So what we do is that now, if we find that a certain particle is subject to this illumination, so what we do is that we're going to switch the same domain volume of this particle, switch that particle from DM to a CFD. We construct a fictitious CFD domain. So these are the two particles representing a CFD cell, occupy the same volume. And then because CFD itself, and we can resolve this temperature field more accurately than, and more conveniently and efficiently than we use DM to resolve it. And so that, and then we can really to resolve that part of that will be melted, and then we directly change it to liquid here. And then if the other part is not melted, and then the laser cells move away, and then it leaves the half melted, and this part will translate back into DM, and it becomes a solid particle here, right? And so in this way, and then we do this switching, and then switching between DM and CFD, just structurally to resolve this temperature field within single particle more accurately. This is what we call a semi-coupled CFD-DEM, and help us to resolve this partial or sequential melting process here. And then the next part is we want to develop a more high fidelity laser source. And then we developed this laser energy distribution using this general Beer-Lambert form plus this ray tracing laser model. Okay, and then we can really to simulate this source, laser source, as a Gaussian or as basically a homogeneous, a uniform one. Uniform one is not realistic. Normally, people use the Gaussian distribution for that purpose. Okay, and this illustration that for example, this source is going to be illuminated vertically down, and then you're going to have this melting process, and then you can see there's a complex energy transfer process, and the laser, the multiple surface, and this multiple surface can partially reflect the energy according to reflection rate. Okay, and this way can have several part reflection to other surface. Okay, and each reflection you observe, you have energy absorption done by the liquid here. Okay, and also you could really get a so-called vaporized region, and also you have a part of this called refracted ray here. So part of the ray will penetrate through and get a refraction here. So this is how the energy, laser energy, is transferred to the liquid and to the metal pole here, right? And this is basically energy input for the metal dynamics, also for this powder vaporation, for the vaporation for the powder motion here. And so there is this laser model is important. As I mentioned that when we do this fusion, so-called transformation process, transformation means that when we melt a particle, solid particle, and into liquid, and then so this is called a transformation. So fusion thing is basically you can get melted from a solid into a liquid, and then so what we do is, as I mentioned, that normally we treat it in a CFD, and in a CFD, and normally we build a fluid model with different viscosity, and then according to experimental determination, and we basically have a so-called fusion zone, and we're at a certain temperature, for example, around 1900 K, and then we transform the viscosity of the fluid model to a typical high viscosity representative typical solid, and then to a low viscosity to a liquid here. Okay, and of course, we can really do it reverse way for the solidification here, right? So this all happened in our CFD simulations. How we really handle this fusion process, fusion and solidification here. And these are the terms that we consider these the temperature equations, including this dissipation, latent heat term, convection, radiation, and evaporation. Okay, we need to rigorously consider all these physical sources and to deal with the process here. And also for the moment equation, we need to consider the Darcy flow, and the surface tension is an important part for the way we show later will be the K-hole dynamics, and recoil force, and essentially is basically a surface tension difference and along the two interface here, right? And also Baragoni forces. There's another source of force and important contributor to this K-hole dynamics here. And regarding again that this we go back to this laser model, and then when we have a laser beam, and then to illuminate the two part of this particle and also multiple here, and so there will be generated some because the energy power, the power is so high, it can really to evaporate part of this liquid into vapor here. And so typically we consider so-called evaporation like this one here. Okay, and so you can generate these are the basically condensed matter, for example, the multiple liquid, and then you generate a thin not thin layer, and then in between the transition layer, and then there will be a vapor layer, and generate some shock wave, and then this is the refined layer of these vapors, and then mixture with this ambient gas, and then the further will be ambient gas here. Okay, so we need to develop such a refined evaporator model to consider the evaporating process here. Okay, and because in such process, and then we need to have a very refined safety mesh to account for that simulation here. And so the additional term for the vibration model will include this advection and the moment equation and temperature equation for that purpose here. So this is the further illustration that how we kind of to consider using this volume of fluid method or use different volume content and to consider the different fractions of the heated metal and other part here, right? And so this is the further illustration how the laser penetrator through this metal liquid, and then we discretize this refraction rays, and then further to consider this attenuated refractor rays, and then also for refraction as well here, and then to have a very refined laser model. This is critical for the simulation of this L-PBF here. And these are the further equations, including this incident ray, incoming ray. As I mentioned, that the incoming illumination ray can be reflected, and then reflection, of course, have reduced the strength and the power, and also have refracted ray. Those all can be calculated according to some theory, and also for each cell, and you have a certain power absorptions for that part, and these are the absorption energies that we sum up that one and to put into the CFD simulation here. And so these are the process that how we can relate to this on the right. Basically, the layering is a powder layering process I showed before, and there will be already there's an existing molten track on the bottom here I showed before here, right? And these are the melting process we simulated. We can relate to scan the powder layer in a recursive way and according to certain scanning velocity and scanning directions, as well as the so-called the track distance, track gap here. Okay, I'll show you again. This is a top view of this melting process, and part of this particle will be partially melted, and then the other particle will be blow away. This is we call a powder motion that is generated by the melting process here. And here, this is the effect of laser power here, and so the laser power magnitude can be important here, and you need to have a proper laser power. Of course, I mean you want to have a stronger laser power, but a stronger laser power will generate deeper keyhole, and this keyhole easily can really spread a lot of surrounding particle away, and then affect there's the printing effect. Also, it generates so-called this roughness, which is not desirable, and also high power also can easily generate the so-called keyhole porosity. But less power normally you can only generate a shallow keyhole, and then it's not efficient here. So a combination of this keyhole, a combination of this laser power and with scanning velocity, and that are some of these printing parameters that we can really choose for the printing effect here. And also another thing is called hatch distance. So-called hatch distance is, for example, when you really go one direction, you go back, and for another track, and then you want really if there's a so-called 1.5 distance, you leave the laser diameter 1.5 and leave a gap here. You can see here in the middle, and then there are some particles unmelted, and this will form a very strong surface roughness, which is not good for the quality. Okay, and if we have the equal laser diameter, and then essentially it's better than previous one, but still have this kind of roughness left here. And but normally people use this a hatch distance defined as we generate a little bit of overlapping for the right and left one, and so we can still convert it to totally melt the center part and generate relatively smooth surface. So this is the comparison. If you have a 1.5 times 125 times of this laser diameter, you generate this particle stacked, or a half is a discontinuity generated, and equal size, and it still have some discontinuities. But if you have this certain overlapping of this one, we call it hatching distance, and this will make the surface much better. So this is a laser hatch distance here. And this is compared with experiments that are, how in practice and it's done. And this is the reporting in the literature here. And also, there are multi-layer simulations. We can also do that. Essentially, we multi this part, and then we leave this part, and on top, and then step 3, and then we layer another layer of these metal particles, and then we roll it. Use the roller to lay it, and then we repeat the printing size. Do that. This is how the multi-layer simulation is done here. Okay, we do some simulation cases. One is we consider this titanium alloy bare plate simulation. Also, the other is basically consider a powder bed simulation. We show different validation cases and also analysis cases here. First thing that we want to benchmark this ray tracing K-hole here. We have these are the top other. We consider that there's a laser source limited vertically. We don't move it, and we just keep continuing to eliminate downwards here. So at the beginning of the top, and you generate a small vapor depression. This depression is called a K-hole. And this K-hole will penetrate through. The K-hole basically is a so-called vapor depression. And this is a generate high-speed vapors inside it, and within this liquid, surrounding is liquid here. So this is the liquid. The pink area is a meltable liquid here. Okay, these are the bare plate here, right? And then so this is the depression and going down forward here, and these are the formed a very deep depression here. This is our ray tracing laser model, and reproduce the same process here. These are the metal pole, and these are the depression K-hole here. And then we also want to benchmark this called a partial melting process here. So these are the illustrations that partial melting works. For example, on the top, if you have a particle eliminated on the top, laser eliminated from the top, and the top will be heated first, and the top will melt first, and then until it ready to melt and wholly, and then you continue to illuminate, and then the liquid can become evaporated, become a vapor here. So this is our simulation process. You have a particle and DEM particle. And then when you eliminate it, now we replaced by CFD cell with the same volume, and then to do this continuous illuminating, called this partial melting and vapor as well here. These are the simulation process that are we eliminated it, and then gradually the top will melted, and the top part will evaporated, and will bottom will melt down here. Okay, as a benchmark case. And so this is how we simulate the process. Now we have a bare plate titanium alloy, and then on top of that we have this metal powder here, and we illuminated by laser source from this direction. And you can see this there's a process again, okay, and then this will generate a so-called K-hole. The K-hole is full of this high speed vapor, metallic vapor. These arrows shows the velocity, magnitude, and direction of this vapor here. This vapor speed is so high, the pressure is also high, generates this depression K hole here. And then the space is limited, and so it's going to escape quite fast from this direction. And then when it escape, it will interact with the surrounding metal powders and generate a powder motion here. Okay. So this is on the right, basically the CFD cell that we illustrate for a backplate that we use a so-called adaptive mesh, dynamic mesh remeshing strategy that around this metal pole and also the K-hole area, and then we use a adaptive final mesh and to capture the whole process in a more accurate way. So here's another illustration that how you can part of the particle is melted here, right? Okay, and then the other metal pole will form behind this scanning direction here, and the well particle is thrown away. And if we recap the whole process, it can certainly show this multi-phase dynamics, multi-phase, multi-way dynamics. You have a laser and generator vapor, and this generator the K-hole, and there the reflection rays, the refraction waves inside here, and this is multiple dynamics. And here they have an ambient gas. The ambient gas interact with this vapor, high-speed vapor, and then the generator is so-called vertex. This vertex can ready to carry on this surrounding particles and form a quite complicated powder motion here. Okay, and this entrained powders can further ready to move in a quite complicated way here. Essentially, that we can ready to we need to seriously consider this the powder particles, metal pole liquid, and metal vapor, ambient gas, metal strata, and the laser source. Those are different ways here. This can be captured in such a model here. Now let's specifically look at the different aspect of this printing process. One would be this powder dynamics. So as I mentioned, the high-speed vapor escaping from this K-hole can generate very momentum, and this momentum will drive the surrounding particles and generate this spattering. And so these are the other experimental observations that those particles can be ejected away from this spattering and splashing way. And this can be important factors that affect this printing quality. Because, for example, some particles, if there is a spattering and into the metal pole, and this will make the metal pole is not homogeneous, and then the printing quality can be affected here. Okay. And so that is the process that we can capture and by such a process here, right? And then this is the further capture of the process. So the escaping of this high-speed vapor will mobilize the surrounding particles, and then to this again that show the evaporation models for the effect for this powder motions here. And this is the feature that is has not really been in the published work, and then no work has really to generate this evaporation and to cause the powder motion here. This is another picture that at this speed captured by this experimental observations, how the powders can be splattering furiously and effective thing here. So this is a illustration that if you're ready to scan from here and then move to the right, and then you can see here the surrounding particles can be sprayed and splattered away. And if you don't have enough source of metal particles, and then the printing quality can be low. That's why it's important. So it's not necessarily that the higher laser power, the fast speed or the lower speed can generate better quality. And sometimes you have really to have a balanced strategy, really to choose the proper power, proper scanning speed, because the ultimate goal you would have a better printing quality. This is the further illustration for the different dynamics. And you can see the vapor escape, and then you generate a certain kind of like different region will be dominated by different interaction forces, and then the mechanism here, right? Okay. I just want to show that in region 1, 2, 3, 4, and then there will be a quite a unique interactions and involved for this process here. Now let's look at the keyhole dynamics that are we want to address. This is an important part, and then indeed the most critical part that are to ensure the printing quality of the 3D printing here. Okay. And so this is the experimental observation how when we laser melting a metal powder, and then the part of this laser will penetrate through the existing strata, and then to form so-called the keyhole. And then first it formed the so-called J-leg, our letter, the letter J, and then look like a letter J here, and form a J-leg keyhole. Okay, and also it's formed because the keyhole support, as I mentioned, is typically it is a depression full of high-speed air, so it's quite a dynamic, it's not stable. So at the bottom part, it can be bulged bigger, but at this part, it can generate a so-called collapsing of the two walls, the surrounding walls. This is what we call a protrusion. So the back wall and front wall can really collapse each other, protrusion. And once the wall on the upper part close in, and then the lower part will be cut off, and then become a enclosed pore. And this enclosed pore can be left, for example, can be left and in the multiple liquid, and then if they left a lot of that, and it will become a defect here, right? Okay. And then the process, in this process also it have certain physical process involved, as we are going to discuss later here. But when this pore is left in the multiple liquid, and once the liquid is cooled down and then solidified, become a solid, and then this become a defect, and seriously affect the printing quality. So this is the observation published in Science. And now let's look at our model. We consider a bare plate, and then subject to this laser melting and laser illuminating here. We use this adaptive mesh, automatic adaptive mesh, and then for this surrounding area, and then this is a comparison of this the vapor and multiple interactions we generated compared with this experimental observation here, right? And then for when the laser melted, illuminated from here, generated the keyhole. These are the front keyhole wall, and these are the back keyhole wall here, and these are the inclined surface, and then these are liquid. Part of liquid will be pushed behind, and then form over the previous the plate surface here. Okay. And then we move on, there'll be more liquid push up, and then there'll be dynamic thing, and then the keyhole will change shape here. And then this will further go on, and then you moved on, and then with this whole process going on here, right? So this is the vapor, so that the vapor and inside this keyhole, and also the metal pore dynamics on the surface and also surrounding it here. And here, this is the other different ways, and really depend on the laser source power, as well as the scanning velocity and the scanning direction here. Okay, And if your power is low, and then your keyhole is not apparent, it's just a small dip here, and then you can generate such a process. Okay, and so, but if your scanning velocity is slow, and then your laser power is strong, it can generate deeper hole, and so this vapor dynamics and with this multiple interaction can be quite different in such a way. As you can see that the printing strategy depends on a lot of factors in such process here. Okay, and then in the different process, and then we we need to consider the thing here. Is a experimental observations published in Science, and how they observe that this is a metal powder, and this is a underlying structure, and then this is I will show it again, that how this G-like keyhole, and then there will be this other keyhole pore left behind this one. This pore will generate a permanent defect here. That's why the 3D printing, the industry, they try to really to have develop a optimal strategy, and they expressed in such a diagram, and the horizontal is scanning velocity of the laser source, and the vertical is the laser power, and they want to have a optimal zone, and where, and then the yellow regions is likely that you have a slow scanning velocity, but a higher laser power will easily generate so-called keyhole porosity, generate defect here. And when you have a relatively fast scanning velocity, well, relatively low one, and in this light blue regions, these are called stable melting process here. And so we want to identify a gap or boundary that in this one, and where somehow the powder can really play a role. And so these are the diagrams that that the industry want to identify, and to really to develop a stable melting strategies and in the 3D printing here, right? So this is what we do in our simulations, and we can really to use a different combination of this laser power and also scanning velocity, and try really to explore the different cases, generate different keyhole, and then with that, and then we can further explore the whole combinations, and then to identify the in such a diagram, VP diagram, we identify the stabilized melting area here. Okay, we can also compare the keyhole depths, and with correlated with the power, and with other inclinations, the printing directions, and it's really to develop the optimal regions. So for different regions, and where would this line up at this correlation here? So this is the power that when we develop efficient computational tool, that we can really do, if it is a high fidelity and calibrated, and then we can do systematic study, and to help us to identify a better printing strategy to help in the practical printing here. Now we have this tool, and this tool is high fidelity, and then it helps us to understand how the keyhole is formed, and how the keyhole pore is formed here. Okay, I want you to show in this one that in our simulation how we demonstrate how the keyhole pore is formed, reproduced in our simulation here. So this is the scanning direction here, right? And we have laser, and for example, pointer slightly tilted and downwards, but moving continues to right here. Okay, and so this is the keyhole pore is generated, and then once the pore generated, and then you have dynamic process. This keyhole pore. You can see this is a protrusion, and then the walls collapse each other, and then you have the lower part. Lower part is left. Once it's left, and then the generator later on will show that the macrojet. Macrojet can relate to sometimes split the big pore into small ones. Split the big pore into some like 3 small ones, and then during the process there are other physics involved like condensation. Essentially, these pores, as I mentioned, the filled with a metallic powder. And the powder, when it's split from this keyhole and into this metal pore liquid, liquid temperature is typically small, is lower than this keyhole. And then when the temperature is lower, and then the vapor will be condensated, and then their volume will shrink. So this is how the keyhole pore is generated. Okay, and then the process of formation, collapse, splitting the keyhole pore. The pore can be splitting and then moved by this the metal pore liquid and along the process here. In the process, we need to consider the fusion and solidification of the liquid part, the particle to the liquid, liquid to the particle, and also we need to consider the evaporation and also condensation. As I mentioned, we need to have a condensation. So this is a this is a comparison with the experimental, again, Popton science on the right here, and how this keyhole pore is a protrusion, is a formation, the J-like keyhole is formed. On the right, on the left is our high fidelity simulation. You can see these are the keyhole, and then part of this one, these other parts that are the laser source will directly eliminate on this part. And so this back wall and the front wall, they are trying to approach each other, and this is what we call a protrusion here. Okay, and if they touch upon each other, this will close in this keyhole. The bottom part will become pore here. Okay, and on the bottom is how the keyhole pore is generated. So in this case, this protrusion is not finished such that the keyhole is continuous. There's no keyhole pore. But on the bottom, you can see here, it generates a keyhole pore and left a keyhole pore behind. This is our bottom, is our simulation. How you can this protrusion and the really close one, and the bigger one can generate a so-called macrojet. We can really see more clearly, and so these are the initial right after this closed in, and then at the when the closing, and this part will generate a high speed macrojet. The speed can be high. This dynamic process, and then will further impact the whole bubble. And then sometimes this is how this high speed macrojet can really split this bubble into several small bubbles. And then this is what we do: have small bubbles and make it shrink. So okay, and so this can be captured by our process. Again, that I want you to show a typical process. You have front wall and rear wall. These are the existing metal pole. These are the keyhole here. Okay, and then you develop this protrusion where the rear, the back wall and this front wall will open to each other and then become smaller, and then here have a necking and closed in, and so the closure of this keyhole will left the bottom part become a pore, and this pore will develop macrojet on certain closing point, and then the macrojet will further split this big pore into smaller part here. Okay, and in the process, condensation can happen. Okay, this is the further illustration here, and it's whole process from the top, and then whole process indicator how a keyhole pore can be generated, and then you can see here from we do this way. This is continuum from left to right, and then these are the front wall, these are back wall here. right? You have a dynamic at the bottom here, and then you have a develop a small so-called mini cohort at the bottom here. This mini cohort and have this dynamics, this liquid from the from the from the real wall part will flow towards the front wall here. This will develop a protrusion at the lower part. This protrusion you can see opposed to each other, and then once when they touch upon each other, they close in all the bottom part here. This bottom part will become a closed in and left inside of this metal pole liquid here. And this metal pole, you imagine there'll be a velocity moved backwards, and this will carry this pole and moved behind here. And during the process, it can really develop condensation and such that its volume will shrink. So the volume will shrink and become smaller. Okay, but sometimes this pole itself can further due to this metal pole liquid motion, and it can be ready to move back to the keyhole and then merged with the keyhole again, such that some keyhole pole can be merged by the keyhole itself, and so it disappears. And so in this way, and they say this is the process, whole process. This one now recovered by this keyhole, and then there's no keyhole pole generated here. Okay, and so in such process, and then I want you to explain more in fun detail that there are multiple physics playing a role here. Okay, and then this is where the recoil pressure and then the continuous protrusion and surface tension all play a role. You can imagine you have a high pressure vapor keyhole. You have this liquid, and so the surface tension can be so important. Surface tension means that for the liquid part, they want you to hold back here, right? Okay, and so when there's a strong like a pressure difference, and then you develop other physical phenomena, and where this recoil pressure and Marangoni pressure plays a role here. Okay, and then how the keyhole pole is generated. Essentially, you have this protrusion and then continued protrusion. You have vertex flow at the bottom part here, and then the surface tension, and then to cut off at this closure part here, and you leave the keyhole pole here. These are the keyhole pole. The high pressure part indicate a keyhole pole leave here. Okay, and so a lot of factors played in to generate a general thing. Here we also quantify so-called recoil pressure at the different parts. So we can see here, one is the protrusion approach to each other, and then you generate a very high recoil pressure. Okay, these are the surface tension occurs. That surface tension around this closed keyhole and also the leave behind holes. And so the mechanism essentially, we have the three-dimensional vertex flow developed in the metal pole liquid, and also continuous protrusion, as I showed here, and also the surface tension. Remember, this is a three-dimensional structure. This only show a cross section we cut off from one side here. These are the frontal. These are the top view here. Okay, and we look at it from the top, and these are the front part, and these are the back part, and how these two protrusion and wall collapse each other here. These are the illustration of the so-called the microjet here. We'll show later, and then when they close the in, and they see the whole pole is formed, and then at this point we'll generate a so-called microjet here. Well, so that next time I want to show that how the pole itself can collapse, can split, and so this process is quite interesting. It involves the so-called vapor condensation. In the literature, there are three kind of different proposals for the vapor condensation. According to the science paper, they mentioned that vapor condensation refers to a rapid volume reduction. For example, when first leave of the keyhole pole is big, right? And you can see here later on, it rapidly reduces volume. The volume becomes smaller, sometimes even disappear totally. Okay, and the disappearance, the vanishing of this vapor, and sometimes people already argue that it's vapor condensation. Okay, condensation and from vapor state and then to liquid state at all. Okay. And then other argument is that you use a equivalent the bubble model to really to predict it here. Okay, and then the other thing that people attributed to the quick pressure drop and then to this condensation part here. So this is our simulation here. Then we identify once a keyhole pole is generated and at this time instance, and then shortly after you can see at this part and this point here, or at this PC point here, indeed, the generator because you can see here when you're ready to split the two bubbles, and then at this part, and then they will generate a high-speed microjet here. This microjet will spread over the surface of this bubble, okay, and then leftwards here. This is the other experimental observations. This is our numerical simulation, and also we plot the contour from this PC to this so-called P-jet here, okay, and then it generates a very high speed microjet. Speed can be up to 45 meters per second here. Okay, and acceleration come up to 86 meters square meter here. And this correlates very well with experimental observation here, right? And then this can be typically captured by our simulation. And then, but it's very hard, indeed very hard to really to be recorded by the most advanced X-ray synchrotron CT in the world here. As you can see here, their monitoring is quite low quality. And so this microjet and condensation explain why the pore can split. Okay, these are the three collapse mechanisms here. And first, the keyhole pore can leave behind, and then become the microjet, and then it can really to split into the three small pores here. Okay, and the other part is that in other cases the keyhole pore won't split, and but it shrink into a small pore here, right? And the third case is that basically the pore itself will shrink in the process because the keyhole itself will dynamically evolve and extend further. Will recapture this pore and then to become a single keyhole again here. So those are the different mechanisms all observed in the experiments, and then we can reproduce their mechanisms in our simulation here. And then we could have also observed the different pore motions, and then this is highly dependent, highly related with the multiple liquid thing. Sometimes the pore can be ready to going down and with the liquid flow. Sometimes it can really flow through this area and then going back and then recaptured here. Okay, and so the influencing factor including the pore position as well as the keyhole fluctuation itself here. Okay, the whole process sometimes random. For example, this one basically. If the shadow, and then they will be mainly carried over by this multiple liquid motions in the pore here. But if the keyhole is deep, and then sometimes will be severely, significantly affected by these keyhole fluctuations here. And also, this is the further illustration how the keyhole pore can split. Okay, and we can really to use this high fidelity things and to understand the whole physics in a better way here. And regarding the keyhole pore formations, and then we can summarize our systematic findings that are to conclude that a lot of five important interconnected factors control their fluctuation, including the vapor condensation, vapor convective shrink, become temperature drop, and then liquid vertex in the metapole liquid, metapole here, and then also other physics like recoil pressure, and also the surface tension and keyhole morphology here, right? Okay. And then there's some conclusion I want to repeat, and we have our published papers that if anyone interested in this one can really to read our paper here. Last part of this this part of the lecture, I want you to see to show a quick results that how we can make use of this high fidelity tool to help us optimize the printing strategy. And so the optimization of parameter in the past experimental studies for this selected laser melting, and essentially they can change the powder layer depths, and then they can also change the parameter of laser beam, and also they use different material and translate to get optimal printing effect here. Again, that this need trial and error approaches. They're expensive and inefficient, and also less rigorous in a way here. Okay, and also people have in the lab they develop adaptive laser power and then adjust the laser power power source power, and then try to want to get or capture the avoid the metal pole, the keyhole pole. And then finally, the strong power generates a deeper keyhole, and easily you can form a pole, form a hole, form a pole. But the less power, the keyhole is too shallow and then it's inefficient. And then once you find that it's likely to generate a deeper keyhole and keyhole pole, you can really adapt to a less power and do it iteratively. You avoid this keyhole pole. So this is how they want to do that. But that control is not easy, and you don't have any mechanism to do that. Okay. And then they said again that when we look at this one here, and when we look at experimental observations, and then how a keyhole pole is generated, and then in conjunction with our simulation, we have developed a so-called mechanism-based optimization strategies. I want to show that we want to look at the physics underlying different keyhole dynamic stage, and then we inject the optimization strategy to try to avoid the keyhole pole generation here. So these are again that we use a bare plate printing case as an example, and then we generate a J-lag keyhole, and then we let this we observe this keyhole protrusion and a keyhole pole are generated. So you can see the protrusion occurs. This is the bottom is better. Protrusion occurs, and then you generate the keyhole. Keyhole basically split here. Okay, so these are the simulations that we do here. Okay, and typically this whole process, the keyhole dynamics process is quite long here. But this keyhole closure also is relatively long duration. But this collapse and the splitting and the motion, their time is quite short here. Okay, and we identify the different stage of this pole generation and also their time instance, and we want to correlate it directly with the practical printing control here. Okay, and so what we do is we look at this stage 2, for example. First, the keyhole closure here. Okay, and then we use a different power to try that, and how we adjust the power and show the way really to will we be able to avoid the closure? For example, if once we find this closure, and then if the laser source is strong, and then this part will become vapor again, and then this keyhole will stay, and then you don't develop a protrusion here, right? And so this is not always stable here. Okay, and when we look at the stage 1, and then at the bottom part, because typically the keyhole pore is generated by the tape part of the keyhole here, and then the dynamics of this expansion, rotation, expansion, and generate the fluid part, and then the continuous vertex, and then backwards. This can be really to control. For example, we have a standard power, and then we reduce the power by half, and indeed somehow it can help us to stabilize this keyhole. And this intensifier double this power indeed is not effective, can actually enhance this power generation here. We look at how we can really predict the stage 1. So we identify the stage 1 may be important, that we should really pay more attention that for the control in the stage 1 rather than stage 2 here. Stage 2 too fast, and then in that sense that it's more challenging to control. And then before you can really put it in the control, that the keyhole pore already this closure happened, and then it generate the keyhole. And so we want to put the control and adaptive control at the stage 1. And so again, that this is the observations that how we can identify, predict the formation of stage 1 here. Okay, and then we look at the geometry and typical geometry, and then according to the time instance, and they want to define some adaptive indices and for the control here, right? And so those are the 3 adaptive indices we have defined based on our numerical simulation, based on our understanding of these mechanisms. One related to deformation of the keyhole itself, and also another is deformation is relative, and then there's another absolute deformation, and then for another index, and also expansion here. Okay, expansion is the bottom part I mentioned, that there's the expansion part here, and this is a very typical one. If this expansion going on, and then it can easily generate a small keyhole tape, and this will be easily generate a protrusion and generate a keyhole here. So we use these 3 indices as a control factors, and then we are doing the printable size, and then we look at their variations, fluctuations, and then we adaptively change the laser source power, and also even the scanning velocity, and then try really to make them stable here. And so again, this shows their oscillation. We want a stable keyhole rather than very wildly oscillator the keyhole here. Okay, so these are some simulated keyhole pore things. One is the keyhole pore expansion. We have a pore generated, and this is another thing here. And now this expansion case. This is the expansion case, and then we have this expansion and the keyhole neck here, and generate this one here. And the bottom is a shrinkage here. Okay, so shrinkage means that the top part will cut down from the tape, and this expansion basically is from a top, and they expand and collapse to the front wall, and generate a very big pore. But a shrinkage case only closed as the tape part generate a small pore here. Okay, and then this is how further illustration how the pore shrinkage occurs. Typically only happening at the taper part, and then when, for example, this part generates a vertex and moves forward, and then moves upward forward, and then keep going, and this keep going, and then the pore still penetrate deeper, and then this rear part and approach the front part also intrude, and then when the two collapse each other, generate a shrinkage keyhole pore here. Okay, and this is the further illustration, and then we can use the expansion index and this volume as a control factor to look at the different size of this shrinkage keyhole and other control here. And once they are opposed to each other, and then in practice we can really use a high resolution control, really adjust the power. And then when this expansion or shrinkage develop towards a closure of the keyhole, and then we can really to adjust the power adaptively and to avoid that here. Okay, and so the optimal strategies trying really to control the deformation index and also control the expansion index, and then adaptively adjust the laser power, and then to do that here. So in order to really for this such optimization strategy works, okay, and then it won't really adversely affect the manufacturing efficiency, and also it stabilizes the keyhole and prevent the keyhole pore generation. So this is the whole purpose that we do here. So this is our further adjustment that we can really to systematically examine that what are the minimum increase in expansion index and identify certain threshold for the different index, and then serve the other practical control here. Okay, so these are the again that and then we can how we can adjust the according to the threshold, adjust the laser power and form, for example, form from average laser power from lower to higher, and then from higher to low. Okay, and for that purpose, this is how we can also measure the keyhole total volume as another thing that with different threshold, and then to stabilize it, and we can also measure the keyhole depths, and then to develop a whole. This gamma basically is a laser power adapting coefficient. We adapted to 90% to 75% of the standard power, and then to avoid the keyhole generation here. So this is how we can really based on our high fidelity simulation, and we understand the mechanisms, and then we identify different formation stages, and then we adaptively adjust the laser power for optimal printing here. Okay, again, these are the printing one here. So now I want to conclude this part, the whole lecture. Basically, we have developed physics-based computational framework of carpet CFD-DEM to model debris flow, and then where we can really capture the five interaction, the debris, particles, debris flow channels, and then particle fluid, and then barrier components. Okay, and this will serve as an analytical tool for particle design for debris flow mitigation. And then we further extend this unresolved CFD-DEM coupling to a hybrid CFD-DEM coupling for different applications. And the second part is that how we really to illustrate that we apply this hybrid CFD-DEM for the modeling of this laser powder bed fusion for metal 3D printing here. And then we illustrate how the multi-physics process involved in this keyhole dynamics, the vapor condensation, the pore motion, splitting, and then further by the end we present a optimization strategy to really control, try to really reduce the happening of this keyhole porosity. With that, thank you.